In this video, I'll be going through the notes for Unit 3, Section 1, the types of bonds. Specifically, we'll be doing a few things in this video. First, we will define the two main types of bonding we'll talk about in chemistry this year. Second, we'll learn about the octet rule, about how many electrons an atom wants. And finally, we'll learn how to identify the types of bonds in different molecules. So first, let's talk about the two main kinds of bonds. Before we do, though, let's talk about bonding in general. In chemistry, we're specifically focused on how matter or stuff interacts. And when these atoms interact, they will sometimes form new materials by bonding with one another. You can see in this image here on the right, you'll see how these solid sphere atoms are being stuck together with a kind of glue. So this is a very visual representation of what's going on. In reality, it's not this material sticking things together, it's part of the atom themselves. But in chemistry, we're really focused on how are these bonds made and rearranged. So what part of an atom bonds? If we take these two images of atoms, the general idea is if we were to try to smush them together, somehow get them to stick together, what part would be interacting first? Well, think about it. If we put these together, those outermost electrons, the valence electrons, are going to be what encounters each other first. Bonds are going to be formed between valence electrons on different atoms. And remember, those valence electrons, they're specifically the electrons in the outermost ring or shell. We previously talked about the quantum mechanical model. In this case, it's probably easier just to focus on the Bohr model and think about that outermost shell. Just like if these two guys crash together, the first part of them that makes contact is the outermost area. It's the same thing with atoms. That outermost area, the valence electrons, are what form those bonds. Specifically in chemistry, we're usually focused on two types of bonds, at least in early chemistry. One are ionic bonds. We'll talk about them a little more later in this presentation. And the second will be something called covalent bonds. But in general, all of these bonds are about how atoms stick together. So first, let's talk about ionic bonding. And just know in a later video, I'll be going through ionic bonding specifically. But for now, just know that ionic bonding is when one atom gives up an electron and another atom takes that electron. So this really is a relationship between two atoms. It's not that one atom is lost forever and another one just appears out of nowhere. It's a transfer of electrons between atoms. When an atom loses an electron, it becomes positively charged. And the atom which gains an electron will become negatively charged. Really, this is all about following that electron. If we look here on the left side, an electron was lost from this atom on the left. Because we're losing a negative charge, our atom becomes positive. And the atom on the right, because we're gaining a negative charge, it becomes more negative. And this example on the bottom shows how sodium can give up one electron to chlorine. Notice that sodium then, it loses that outer ring, and chlorine fills its outer ring. Sodium likewise becomes positively charged because it lost an electron, and chlorine becomes negatively charged because it gained an electron. And once that electron transfer occurred, they kind of act like magnets. The positive sodium is attracted to the negative chlorine, and they stick together. And we really show this sort of like solid sphere atoms a lot of times. Contrast that with covalent bonds. Covalent bonds are when two atoms share their electrons. And our example to the right is going to show carbon and oxygen sharing those outermost electrons. We can see these two single electrons in the valence shell of oxygen on the left and on the right, pairing up with the single electrons of carbon shown as X's here. They're being shared between both atoms. And that really gets down to the name of covalent. Covalent, meaning the valent electrons are cooperating or working together. Now, why did these electrons get transferred? Well, it was to satisfy something called the octet rule. The octet rule is pretty simple. It basically says that an atom will almost always prefer to have 8 valence electrons. How can we remember octet rule? Well, a couple clues that we're used to are anything that help us remember oct, meaning 8. An octopus has 8 legs, and an octagon has 8 sides. An octet rule is a full shell of 8. Notice that some atoms, like neon, they already have that full shell of 8. And so that makes them very, very stable. They already satisfy the octet rule. On the next slide, I'll go into one exception about this, as well as talk about this trend, such as with neon. So let's take a look at the periodic table, but call out the Lewis dot structures for these atoms highlighted, the S block and the P block of atoms. Notice that based on the column, we can see there's a pattern of the Lewis dot structures. Every column, we're adding one electron. So as we go to the right, we'll see our atoms gain one electron in their Lewis structure. The general exceptions to this octet rule are really our first few elements, our hydrogen, our helium, and also our lithium, beryllium, and boron. The reason these are exceptions is because they actually only need 2 electrons, because a lot of times they go down to that first shell. And remember, that first shell can only hold 2 electrons. So hydrogen, it really only wants one more electron to fill up its shell. Helium is stable. Lithium, as pictured here, it could fill up this second shell, but it's much easier for it to lose the outer electron and just go down to 2 electrons. However, all other atoms on this table here on the right, or on the left, excuse me, are more or less going to satisfy the octet rule, although it does get a little more complicated when we get into the d orbitals. Now, I also said we would go over our one kind of trend here as far as stability. Notice that these atoms on the right side of our periodic table, helium through radon or Rn, other than helium, which is satisfied with 2 electrons, they all already have their full octet. These are called our noble gases, and they're noble because they don't react with anything. They're kind of held separate from the other elements. Because they have a full shell, they usually don't react. Now, a couple examples of ionic bonds or ions satisfying the octet rule. If we look at sodium here, and we'll look at calcium too at the same time, sodium has 1 electron in its outer shell. If it loses that electron, it'll have a full second shell here and be stable. If calcium loses its outer 2 electrons, it'll have a full third shell as seen here, which also makes it stable. Oxygen has 6 valence electrons, so if it gains 2, it will have a full octet. And fluorine, super close to a full shell, if it gains just 1 valence electron here, it'll have a full octet. So let's talk really quickly about ionic versus covalent bonds and the octet rule. Note that ions, they end up all having full outer shells. It doesn't matter about their partner ion, not exactly. Every ion is going to have a full outer shell. As shown here, when sodium transfers an electron to chlorine, sodium ends with 8 electrons in its outer shell, and chlorine ends up with 8 electrons in its outer shell. Covalent bonds, we have to look at the shared electrons as sort of belonging to both atoms. If we look just here on the left side, oxygen in its valence shell will have 1, 2, 3, 4 electrons that it owns completely, and 1, 2, 3, 4 electrons that are being shared with carbon. But in total, it still has 8 electrons in its outer shell. If we look at carbon in the center, all of its valence electrons are shared, but they still count towards satisfying that octet rule. So covalent bonds, the shared electrons count towards both atoms. And now let's get into the actual skill for this video, how to identify types of bonds. The easiest way to identify types of bonds is to use the periodic table, but look at it as a separation of left and right using this kind of black staircase here. Metals on the periodic table will be everything to the left of that staircase, except for hydrogen. Hydrogen's kind of weird. Non-metals will be on the right side, and we count hydrogen as a non-metal. And there are a few yellow metalloids here. Those are elements that don't really fit into either category. Our rule for identifying types of bonds using this kind of left-right idea is that an ionic bond is formed when we combine an atom from the left with an atom from the right. If we combine a metal on the left with a non-metal on the right. Some examples would be lithium and nitrogen or magnesium and oxygen. Notice that these metals and nonmetals together, they're going to be our ionic bonds. Our covalent bonds are formed between only nonmetals. So for instance, if we look at C and O, notice that they're both on the right side, so that would be a covalent bond. So which kind of bond will the following combinations of elements form? Try to find them. If you'd like to pause the video and try to do this on your own, feel free. And I will now go through these. If we look at sulfur and fluorine here, if we find them on the periodic table, we'll see they are both on the right side. They're both nonmetals, and therefore these make a covalent bond. Magnesium and bromine. Find magnesium here on the left. We find bromine here on the right. Because it's a mix, these are going to be ionic. And aluminum and oxygen. Aluminum is just to the left of that staircase, and oxygen is to the right. So because it's a mix, we're going to say it's ionic. So altogether, sulfur and fluorine are covalent, magnesium and bromine are ionic, and aluminum and oxygen, because they're on both sides, are ionic. Now that's kind of a simple view of things. A somewhat better way to look at things is to consider the difference in something called their electronegativity. Now, electronegativity is just a numerical measurement of how much an element in a bond wants an electron. Elements with higher electronegativities will pull on electrons more, and electrons with lower electronegativities will pull on electrons less. If we look at something like fluorine here with a 4.0, that has the highest electronegativity, which I'll abbreviate here as En. If we look down to the bottom left, though, say francium, these have especially low electronegativities. And that's the general trend on the periodic table. As we go up and to the right, we go from low electronegativities to high electronegativities. And remember that electronegativity is how much that atom is pulling on the electrons in a bond. But one element's electronegativity does not tell us much. It's more about the difference in the electronegativity that tells us what kind of bond will be formed. In my first example, lithium, it's going to pull on its electrons, but it has a low electronegativity, shown here with the 1.0, that's pulling pretty weakly. Contrast that with a partner such as oxygen, which is pulling much more strongly. Because the difference in their pulls is relatively great, lithium's probably going to lose its valence electron to oxygen. And because it's losing its electron and oxygen is gaining the electron, we make it an ionic bond. Notice in a situation like oxygen sharing with another oxygen, they're both going to be pulling strongly. So there's no difference in the pull. They both want the electrons. Because they're going to pull it equally, they're going to share their electrons and make their covalent bond. So again, it's not about one pull. It's about the combination of the two. Is there a big difference in the pull? And really, we have three kinds of bonds here, and they really go on a spectrum. Ionic is when the difference in electronegativity is greater than 1.8. That's when electrons are going to be completely transferred from one atom to another, therefore making an ionic bond. Covalent is when the difference is super small, when it's less than or equal to 0.4. In these cases, the electrons are being pulled in both directions, but rather equally, therefore they're going to be shared equally, and we call that a covalent bond. And if our difference is between 0.4 and 1.8, we're going to see that that is something we call a polar covalent bond. The electrons are still being shared, but they're being shared unequally. One atom is pulling harder on those electrons, and it feels their effect more. So really quick, what kind of bond will the following combinations form? I'll do the same bonds as last time. If we look at, say, sulfur and fluorine, we know from our previous trick that it's going to possibly be covalent, but we want to find the difference in the electronegativities. I'll do that up here. Fluorine has an electronegativity of 4.0. Sulfur has a different electronegativity of 2.5. And if we find their difference, if we subtract them, we'll get a difference of 1.5. As we saw in the previous slide, this falls in our polar covalent region. Fluorine is pulling much harder than sulfur, but they're both still going to share those electrons. They're just going to share unequally. If we look at our next example, magnesium and bromine, magnesium is 1.2 and bromine is 2.8. Our last trick suggested that this would form an ionic bond, but let's see. Magnesium has an electronegativity of 1.2, and bromine has an electronegativity of 2.8. Now notice that this is going to give us a negative answer. It should give us negative 1.6. But remember, we don't really care about the sign. We're more concerned with how much of a difference is there. And the difference in this case is just 1.6. So even though it's negative, we just kind of treat it as if it was 1.6. Could be positive, it could be negative. It's still 1.6 of sharing. And that puts us in the polar covalent region. They're being shared, but very unequally. Bromine's pulling a lot harder on those electrons. And finally, let's look at aluminum and oxygen. I'll do this down at the bottom. I'll do it in the same order. Aluminum has an electronegativity of 1.5. Oxygen has an electronegativity of 3.5. And the difference will be 2.0, which puts us at ionic. Because oxygen is pulling more, oxygen is going to take the electrons from aluminum and become negative, and aluminum will lose its electrons and become positively charged. Now, really quickly, I'm going to go back to the last slide. Really, these numbers, 1.8 and 0.4 that we've used, there is some disagreement. Some chemists will use 1.7 as the distinction between ionic and polar covalent. Just know that all of these bonds, they're kind of on a spectrum. As we go from similar pulls between the elements, similar electronegativities, we go from bonds that are more covalent all the way to more ionic. So it's not like at 1.8 things just change. That's simply where we set our scale. And those are the notes for Unit 3, Section 1, the types of bonds.